All right, so let's jump right in. So this talk is really about multivariate polynomials, certain properties of multivariate polynomials. So on this slide, I'm going to introduce sort of the main players and the main question of the talk, and then we'll proceed from here. Okay, so in this talk, we're going to be focusing on homogeneous polynomials of degree 2D in n variables, and I'll call these forms for short. Okay, and I'll always use degree 2D, so we'll always be considering even degree polynomials. All right, and there's two key properties of these polynomials that we're going to be interested in this talk. So one is convexity. All right, so we all know what convexity means. In particular, because polynomials are continuous, convexity, it just means midpoint convexity. Okay, is equivalent. And one thing you can observe immediately from the definition of convexity, all right, is that if you're a form, so a homogeneous polynomial, and you're convex, then you must be non-negative, right? So you can check this by putting y equals negative x into this definition of convexity and using the fact that forms have to be even. Okay, so convex forms are always non-negative, all right? And so what are our favorite non-negative polynomials? Well, those are sums of squares, okay? So a polynomial, a homogeneous polynomial is a sum of squares if it's a sum of squares of other polynomials, okay? So, and what's the main thing we know about sums of squares is that, well, sums of squares are certainly non-negative, okay? They're our favorite non-negative things. And some non-negative forms are sums of squares, but not all non-negative forms are sums of squares. And so the underlying question behind this talk and this work, which is a question that's been around for a while, of course, is the question of, well, convex forms are non-negative. We like convexity. Sums of squares are our favorite non-negative things. Are convex forms always sums of squares? Okay, so these are the main players. Forms, so homogeneous polynomials. Convexity implies non-negativity for forms and sums of squares. So are convex forms always sums of squares? All right, now I'll put you out of your misery very, very quickly. So the answer is no. The answer is no. Convex forms are not always sums of squares. Greg Blekherman showed this sort of, I guess, probably 2012 is a published version, but there's older versions out there. So Greg showed that convex forms are not always sums of squares. Right? And he showed this via a non-constructive argument. So it's an argument where it essentially takes compares the volumes of slices of convex forms and slices of sums of squares and shows that there have to be convex forms that are not sums of squares. And what's the main punchline of this talk and this work that I'm describing today is giving an explicit example of a degree 4 form that is convex but not a sum of squares. And this degree 4 form will happen to have 272 variables. And we'll see where the number 272 comes from a bit later. Okay, so that's really the plan for the talk, is to sort of get to this explicit example and discuss a bunch of questions at the end related to this the question of when convex forms are sums of squares. Okay, so just to give maybe a tiny bit more context for this question, I think already it's natural from the point of view of saying, well, whenever I have a nice family of non-negative polynomials, it makes sense to ask when they're sums of squares. But just to give sort of maybe some other motivation for this question, or another way to think about where this question might make sense. So, why do we care about convexity, particularly from an optimization point of view? Is of course a very, very natural assumption in optimization. And in many ways, we can think of convexity as an assumption under which local optimization methods at some level work, right? So local optimality implies global optimality. And so you can do local things and get global results. So that's kind of perhaps one reason why convexity is of interest. And okay, sums of squares is a natural sufficient condition for non-negativity. It's sort of, in some sense, these are the prototypical non-negative things. And at least seems to me that real algebraic geometry is, the inequalities in real algebraic geometry really are built out of sums of squares in some sense. From a computational point of view, sums of squares are very nice. So if you give me a form and ask me whether it's a sum of squares, at least in principle, this is something that we can verify by solving a semi-definite feasibility problem, so a semi-definite programming problem. And of course, you can do much, much more than just check sums of squares, but this is the kind of the basic connection to semi-definite programming. And so sort of sums of squares gives a computational approach to polynomial optimization that perhaps many people have seen, but perhaps not everybody, where if I want to say minimize a form or a polynomial P, for example, I could instead try to maximize a lower bound on that polynomial. And one way I could do that is to try to find the biggest amount that I can subtract off my polynomial for it to remain, okay, non-negative. That would optimize my polynomial, but I could do something more tractable and ask what's the biggest lower bound I can subtract off my polynomial for it to remain a sum of squares. Okay, and this is something I could try to solve by semi-definite programming. And so one sort of question you might ask then is okay, so what if I start with a convex form P, right? Does that, so somehow optimization of that convex form is easy, right? I mean, at least it seems like it should be easy. Should be able to do a local descent method and optimize that form. Okay. And on the other hand, I have this other nice sum of squares based method for trying to optimize things. And I guess the question is, are polynomial optimization problems that are easy because of convexity sort of also easy from the point of view from sum of squares? Okay, and so one thing we could get from this answer that there are convex forms that are not sums of squares is this would give you examples of polynomial optimization problems, okay, that are easy from the point of view of convexity because they're convex, but sort of difficult from the point of view of sums of squares because, okay, if I have a convex form, its minimum value is 0. Okay, plug in x equals 0, that gives me the minimizer. And if the form is not a sum of squares, then somehow the sum of squares based approach to polynomial optimization will not be exact in this case. Okay, so that's some context. And so now let's look at what is known about this question of when a convex forms sums of squares. Okay, so what's the sort of state of the art at the moment? So there's some positive results, which is good. So kind of we've seen that convexity of forms implies their non-negativity. And there's also classical results about when non-negative forms are sums of squares. Okay, so non-negative forms are sums of squares when your forms have two variables. Remember, we're working with homogeneous polynomials here. So this is the basic kind of the univariate case. Non-negative forms are sums of squares when the degree is 2, so quadratic forms, and non-negative if and only if they're sums of squares. And then there's this other exceptional case that non-negative forms are sums of squares when n equals 3 and the degree is 4, so ternary quartic forms due to Hilbert. All right, so that's kind of just from understanding when non-negativity is equivalent to sum of squares for forms. There's this other sort of remarkable and very interesting, very recent work by Bashir al-Qadir that shows that if you look at when a convex forms sums of squares directly, there's a new case. So he's established a new case that if you look at quaternary quartic forms, okay, that are convex, so convex forms in 4 variables of degree 4, these are always sums of squares. Okay, so this shows that this question is kind of more is going on here than just equivalence between non-negativity and sums of squares. All right, so this is on the positive side, this is what we know. What about on the negative side? We've got basically up till now, we have Blekherman's result. Okay, so a bit more precisely, what Greg's result says is that if you fix the degree that's bigger than or equal to 4, okay, then you can find a large enough n so that once you have more variables than that, at least as many variables as that n, and you're in this degree, then there exist convex forms that are not sums of squares. And if you kind of go through the proof and you look at, say, the quartic case, it turns out that the argument requires n to be, I don't know, about 270, some huge number to guarantee existence. All right, so that's what we've known up until now. Okay. All right. So now I'm going to kind of transition from what are the questions into sort of what is the approach I'm going to take to try to come up with an explicit example. Okay. And so what do we need? We're looking for an example of a form that's convex and not a sum of squares. So we're going to need to be able to verify both of these properties. All right, so we're going to start with how could we verify convexity? So the first thing we might do is, so we need somehow, if I'm going to give you an explicit example of a convex form, I need to be able to convince you that it's convex, one way or the other. And so one approach is to use, for example, a natural algebraic sort of sufficient condition for convexity. Right? And so the first thing we might reach for is a nice property called SOS convexity, or sum of squares convexity. And this essentially takes the definition of convexity and changes the inequality into a sum of squares condition. Right? So for example, and there's a number of different equivalent ways to state this, but a form P is SOS convex if this midpoint convexity inequality is a sum of squares in the variables x and y jointly. Okay, so this implies convexity. So maybe this is going to be useful for us. But in fact, it's not useful for us, because it turns out that if a form is SOS convex, then it has to be a sum of squares as well. And you can see this by, again, restricting to the subspace y equals negative x. Okay, in that case, the left-hand piece is just going to be p of x, and the right-hand piece will just be 0. And this implies that this form will be a sum of squares. Okay, so kind of verifying convexity by using SOS convex examples is not going to work. So this also means that any example we come up with is going to be an example of a convex form that is not SOS convex. Okay, and these sort of already interesting objects that were sort of completely classified on sort of the situations of when SOS convexity and convexity coincide by Pablo and Amirali Ahmadi some years ago now. Okay, so SOS convexity is not going to work for us. And there are variations on SOS convexity, sort of with multipliers and so on. But sort of these are possibly not going to work for us, or maybe not going to be the most appropriate sort of approach to take, not the approach we'll take. So instead, we're going to look at a different sufficient condition for convexity. And in fact, this is the sufficient condition for convexity that Greg uses in his existence argument. So it's probably a reasonable place to start. So what does this say? This says that if I take a form P of degree 2D, and it's bounded above and below by the sum of the squares to the power d with some scaling, then the form is convex. All right, so another way to think about this is to think about sort of dehomogenizing onto the sphere, and to say this is the same as saying that if a form P takes values between 1 minus 1 over 2d minus 1 and 1 plus 1 over 2d minus 1 on the unit sphere, then the form is actually convex. So it's kind of, so what's the intuition behind why this makes sense? It's really because the norm to the power 2d is kind of somehow in the middle of the cone of convex forms. And so you'd expect that there's some ball around that form, the norm to the power 2d, where everything is also convex. And this is kind of saying that if you take a ball in infinity norm on the sphere of size 1 over 2d plus 1 over 2d minus 1, then that stays inside the cone of convex forms. Okay, so it's kind of the geometric intuition for why something like this makes sense. So we're going to use this second sufficient condition for convexity. And one of the reasons why is that this doesn't care about the number of variables. Okay, whereas sort of conditions based on sums of squares tend to be quite good when the degree is large, and not so good when the number of variables is large. So this sufficient condition is kind of probably conservative in terms of degree, but not so much in terms of number of variables. All right, so this is how we're going to verify convexity of our form. We're going to relate it to these kind of inequalities on the sphere. And this leads us to thinking about optimization of forms on the sphere. Okay. So let's now kind of spend a couple of slides sort of forgetting about our original question and thinking about polynomial optimization over the sphere. Okay, so I'm going to, or optimization of forms over the sphere to be precise. So I'm going to give you a form P, and we're going to try to find its minimum value over the unit sphere. Okay, so this weird plot on the right is meant to be a kind of polar plot of the values of a polynomial on the unit circle. And you can see that, okay, there's some minimum value here denoted P. Right, so if the degree is 2, this is kind of easy. It's a symmetric eigenvalue problem. But if the degree is at least 4, then in general, these problems can be hard. It's a very rich class of optimization problems. And just to give you an example of the kind of weird and wonderful things that are in here, and this is essentially due to Motzkin and Strauss, though they don't write it this way, and it's a very, very standard example. We can assign with any graph G with vertices V and edges E, we can assign a quartic form, all right, by summing over the vertices xi to the 4 plus something to do with the edges, okay? And it turns out that the minimum of this form over the unit sphere is in fact 1 over the size of the largest independent set in the graph. So if you don't know what that means, it's not really important for the talk, but it's some quantity related to a graph that is, it's sort of a hard quantity to compute. All right, so somehow we can encode these hard problems in optimization of quartic forms over the sphere. This is well known, but just sort of introducing this to give you a sense of the richness of this class of problems, and also because we'll come back to it very briefly in a second. Okay, so this is polynomial optimization on the sphere. There's a natural sum of squares relaxation of this problem. It's more or less the relaxation I wrote before. And this gives us a kind of tractable way to compute lower bounds on the minimum value of such a form over the sphere. Okay, so how do I do this? Well, I try to find the biggest gamma I can so that my form minus gamma times the norm to the power 2d is a sum of squares, right? And this will in general give me a lower bound on the minimum. And so we could measure the kind of a sort of approximation type, multiplicative approximation type quantity related to this optimization problem that I'm going to call gap in this talk. It's probably not the greatest name, but that's what I'm using. This is where I sort of take the maximum value of the polynomial minus this lower bound divided by the maximum minus the true minimum. This will always be bigger than or equal to 1. And how far from 1 it is shows us kind of how bad the SOS relaxation is. All right, and so for example, it's an exercise, not super easy, not super hard, to show that this gap for all of these polynomials that come from graphs related to computing the inverse of the stability number, the gap is always at most 2 for any graph. Okay, so somehow you actually get pretty small gaps in that case. And you could take, this becomes a kind of fun game. You take your favorite form that's perhaps difficult, not a sum of squares, and ask, what is its gap value? And so if you go and compute this for, say, the Motzkin form, which you may have heard of, it's a classic example of a form that's not a sum of squares, you get something remarkably close to 1. That's, I think, the message here. Our favorite examples are actually give values remarkably close to 1. So there are general upper bounds on this gap value, particularly work of Zhao Ni and Fang and Hamza Fawzi, who's, I think, on the call here somewhere. So have given general upper bounds on this quantity. As far as I can tell, there's not a great amount in terms of explicit examples that show this gap is large. So we sort of have general upper bounds that show convergence rates of the sum of squares hierarchy, but a little bit less in terms of explicit examples on the other side. Okay, so this is my quick rundown on polynomial optimization on the sphere and the quantity we're going to be interested in. All right. So why do I care about this gap quantity and sort of in terms of my original question? Remember, my original question was to find a form that is convex but not a sum of squares. So the idea is that I want to translate instead of convexity, I want to use sort of Blekherman's condition of being close to 1 on the unit sphere. Right? So I want something that's kind of close to 1 on the unit sphere, right? Which is kind of, if you like, controlled by quantities p mean and p max. But not a sum of squares. All right, so I want it to be difficult to certify the maximum and minimum values of my form on the sphere using sum of squares. This is sort of the intuition. So in some sense, what I might want is a form that is kind of hard to certify bounds on it on the unit sphere. And that's in fact exactly, if you take sort of Blekherman's condition and you take the quantity gap and do sort of a little exercise, you come up with the following statement, which is extremely useful for what we want to do. Okay, so if a P is a form of degree 2D, so even degree 2D, and this gap quantity for P is bigger than D, then by shifting P by a multiple of the norm to the power 2D, you get a form that's convex but not a sum of squares. Okay, so so this is kind of the main engine we're going to use. And so in fact, we're going to really be focusing on finding a form for which this gap quantity is bigger than half of its degree. All right. So once I've sort of realized this, I was like, oh, well, I'm going to go and hunt around in literature for what people know about forms with big values of this gap. And of course, I first was like, well, these forms coming from graphs that show that, you know, polynomial optimization on the sphere is NP hard. Surely these would be great examples, but the gap is less than or equal to 2 in that case. And the degree is 4. So these do not give us examples. Things like mods can give us pathetically small gaps or impressively small gaps. And there's really very few explicit examples out there. In fact, very few at all. The other thing that you can find out in the literature is random examples, and showing that random examples give large values for this gap. But this, in some sense, is kind of the same thing as Greg's argument about volumes of convex forms. I mean, so it didn't really help in finding explicit examples. All right. So now what I'm going to do for the next section of the talk is at least sort of try to show you what the example is that I came up with. Okay. Where we're going to start is with, in actually an extremely unlikely place. So where I'm going to start with is the Cauchy-Schwarz inequality, which I think many of us think of as the prototypical example of a sum of squares. Remember, we're looking for something that's not a sum of squares. Okay, so the Cauchy-Schwarz inequality, as I think we all know, it bounds the inner product of two vectors by the product of their norms. Here we're squaring everything in the inequality to get something that's a nice quartic form. And so we all know that the Cauchy-Schwarz inequality is, gives us this form that's non-negative, as we see here. If we think about this as restricted to the unit sphere in 2k variables, then the minimum value is 0. Okay, take orthogonal vectors x and y, and the maximum value is 1/4. Okay, just because of the scaling that's on the sphere. Okay, and this is not going to be our example, because in fact this Cauchy-Schwarz form is a sum of squares. One way to see that is to write it as a determinant of a 2x2 sort of Hermitian matrix like this, and expand that determinant using the Cauchy-Binet formula. So this will give us a sum of squares description. All right, so this looks like a terrible place to look for an example, because it's already a sum of squares. But it turns out there's a kind of bigger family of Cauchy-Schwarz inequalities. There's, we looked at the one over the reals there, and there's also a Cauchy-Schwarz inequality for vectors with complex entries, for vectors with quaternionic entries, and for vectors with octonionic entries, right? And so this is where the connection with the previous talk perhaps comes in. So the octonions made a brief appearance in Frank's talk, and they'll make something of a less brief appearance in this talk. All right, so we can take any of these four, finite dimensional real norm division algebras and form a sort of a biquadratic form, a quartic form that is this kind of Cauchy-Schwarz form. Right? And so what does this mean over one of these more esoteric objects? So maybe I didn't make a slide for this, say briefly sort of how we can think about the octonions for the purposes of this talk. So think about the octonions as linear combinations of of an identity unit and 7 other units. So think about these as generalizations of I in the complex number case. So linear combinations of these things. So you get an 8-dimensional sort of algebra. I'm going to define, there's a multiplication table among these units, all right? And the catch with this multiplication table is it's not just as non-commutative, but it's also non-associative. So it's kind of a bit confusing to work with. There's a conjugation operation where I keep the coefficient of the identity sort of as it is, and I negate all the coefficients of all the other 7 units, right? And so these are the key things you need. And then once I have these, I can take a list of octonions that I can define, the norm squared by taking the sum of the octonion times its conjugate, which gives you something that's a real number, a real positive quantity. And it's really just the sum of the squares of the coefficients. And there's this kind of octonionic sort of bilinear thing where you take the sum of xi conjugate times yi. Okay, so like the first quantity is a real number, this norm x squared, and the brackets xy is an octonion. All right. So, all right, so this gives me some generalization of the Cauchy-Schwarz form. Again, its minimum value is 0. Okay, so the Cauchy-Schwarz inequality still holds. And the maximum value is 1/4. So the same inequalities hold on this form. But it turns out that in the quaternionic and octonionic cases, these forms are no longer sums of squares. So this Cauchy-Binet argument fails in these cases. Okay, so these maybe are potentially interesting examples to investigate. And so what I did is I started really computing with the quaternionic case because it's smaller and easier to deal with. And what I noticed is that as you increase the value of k, the length of the vectors, I noticed that the gap was growing. Okay, and this is very interesting to me. But it turns out the gap doesn't grow enough in the quaternionic case to get above our magic value of 2. Remember, what we're looking for is a quartic form, for example, that has this gap quantity, this relative error measure to be bigger than 2. So the Cauchy-Schwarz form over the quaternions doesn't work, but it turns out that the Cauchy-Schwarz form over the octonions does. All right, so this Cauchy-Schwarz form over the octonions, we can think about the octonions as really just, in terms of its coefficients, as 8 real variables. I've got 2 octonionic vectors x and y here, each of length k. So this gives me 2 times 8 times k equals 16k real variables. So this is, I think of this as a form in 16k real variables. And you can write this thing down very explicitly. I mean, I haven't written it explicitly on the slides, but you can write it very explicitly. And it turns out what you can show is that this gap quantity for these forms, actually if k is bigger than or equal to 16, this gap is given by 15 over 8 over k plus 7. And if you plug in k equals 16 into that expression, you will get 15 over 7.5, which is 2. And if you plug in anything k equals 17 or larger, you'll get something strictly bigger than 2. Okay, so this gives us our example of a quartic form that has this gap quantity bigger than 2. All right, once I choose k bigger than or equal to 17. All right, and so the corollary of unwinding some of the things we've said before is that if you take your Cauchy-Schwarz form and you add 1/4 times the sum of the squares, I'm missing a square there. It should be the sum of the squares all squared. This gives me a quartic form in 16 times 17 equals 272 variables that is convex, but not a sum of squares. Okay. Yep. So I'm not going to say too much about, I've said a lot about some parts of the proof, particularly how do you deal with the convexity part. I'm not going to say too much about how do you show that this form is not a sum of squares, apart from just drawing some silly cartoons. So at some level, if you give me a form and I want to show that it's not a sum of squares, all I have to do is solve a semi-definite programming feasibility problem. All I need to do is find a separating hyperplane between the cone of sums of squares, which is a nice closed convex cone, and this form Q, which is meant to live outside. Okay, but the a problem with this is that if you do this naively, the sum of squares, the SDP is going to have matrices of size 273 choose 2 by 273 choose 2, which is on the big side for SDP solvers. Okay, so what do we do? And well, of course, we exploit symmetry. So this form Q has a very large, very interesting symmetry group. It took me quite a while to figure out exactly what the symmetries were. Well, it turns out that there's an orthogonal group action on the k elements of the vectors, but there's also the symmetry group of pairs of octonions, which turns out that there's an action of the spin 9 group, which is the double cover of SO9 on pairs of octonions. And this gives me a group that actually leaves this whole form invariant. And if you do symmetry reduction with respect to this group, so you get actually a linear programming feasibility problem in R3, which is easy to directly get a separating hyperplane. And so what do I mean by symmetry reduction? All I want to say is that what you can do when you've got very symmetric semi-definite program is you can restrict to a subspace of points that are fixed by the action of the group, of the symmetry group. And so really all we're doing is we're looking at the sum of squares cone intersected with all the polynomials or the forms that are invariant under this group action, and you end up with a very simple polyhedral cone. You can directly check somehow using a small LP that Q is not in that cone. Okay, so to wrap up, I'm running very much out of time. Just want to ask a few questions that are naturally raised by this. So really come up with some explicit example of a convex form that's not a sum of squares, something that people who've raised this question have been sort of asking for. But I don't think we've really, it's in some ways a bit unsatisfying. I mean, I'm not really sure I understand really why does this example work, and I don't really know how to generate with confidence other examples like this. So what seems to be crucial is that there's sort of a family of non-negative things, indexed by a number of variables that you get a sort of a proof in one hit that they're all convex, but that the sum of squares bounds get worse as the number of variables increases. And so there may be other ways to produce such examples. This is just an example in degree 4. I don't know examples in higher degree. Again, we know they should exist. And in some sense, they should be easier to find. But I certainly don't know any systematic construction procedure to take a convex form that's not a sum of squares and produce another one of higher degree that has both of those properties. It's easy to produce sums of squares of higher, or not sums of squares with higher degree, but it's not so easy to do that in a way that preserves convexity. Okay. And of course, the overall question behind this is, it'd be nice to know exactly which degrees and number of variables convexity and sums of squares, or convexity implies sums of squares. That's on the convex versus sum of squares side. And really what you've noticed is that this talk was less about that question and more actually about polynomial optimization on the sphere and this quantity gap. So, a very interesting thing would be to know what is, for every n and degree 2D, what is the biggest value that this gap can take. So we have some upper bounds, but we don't really have, I think, very explicit examples that give lower bounds, particularly, yeah, so that's I think an interesting general question. One thing you can do with this connection that's quite interesting, I'll just leave you with this, is that we can also take it in the other direction, right? So we can take Al-Qadiyah's interesting result that says that convex quaternary quartics are always sums of squares and sort of run our arguments backwards. And so if you do this, well, we know that if convex quaternary quartics are always sums of squares, then for quaternary quartics, this gap quantity must be always less than or equal to 2. Because if it wasn't, we'd get a counterexample. We'd get an example of a convex quaternary quartic that was not a sum of squares. And so this gives us also a kind of, this is the strongest bound out there as far as I know, for the specific case of quaternary quartics on this gap quantity. It improves on existing bounds in the literature. Of course, those existing bounds hold in much greater generality, so it's not a very fair comparison. But it would be interesting even in very small specific cases to understand really what is the worst case values of this gap quantity. Okay, so to summarize, we've investigated this question of when are convex forms sums of squares, and given the first explicit example of a convex form that is not a sum of squares. All right.
Great. Thank you so much, James, for a very interesting talk. Any questions or comments? Let me start. So one thing, so do you have a sense of what would be the most, or let me not say the, like the most symmetric form that you could, that would still have this property? Somehow, like another way that you can start thinking about this is that, like, okay, let me, of course, if you have the full orthogonal group, like, this will not work, but how much can you go down until you can start breaking symmetries until, like, until some example appears, right? Like in your case, your form is extremely symmetric, right? But
right, and still as an example.
Yeah, but is there something, for instance, that's a little bit more symmetric than that, and it will still have that property?
Yeah, I mean, I don't know, of course. This is really the only example I know. But yeah, I think that's an excellent question.
Or let me perhaps ask
of...
the convert. Well, no, I guess I think it's what you said, that it's three-dimensional, right? If you constrain that symmetry, then the space of forms is three-dimensional, right?
Yep, that's right.
I see.
Yeah. So
and there's no obvious super group of that, right? Like,
I mean, there might be, yeah.
Like even if it was ON cross ON, for instance.
Then I don't think you would, because you'd be then in the, probably you'd get the Cauchy-Schwarz over the reals type form. I mean, not that, but that would, I mean, I think you don't have enough interesting things that can happen somehow.
I see.
Yeah.
It's very interesting that it's only three-dimensional, like in that.
It's a bit shocking, actually.
Yeah. Other questions or comments?
So James, I have a silly question. Do you think this number 3 has anything to do with the cone of 3x3 Hermitian octonic matrices, so the exceptional symmetric cone?
I don't say that with great confidence, but because there's so many bizarre, weird things that happen with octonions that I've just started to be learning about. But I think maybe picking up on that 3x3 octonionic case, I mean, there's a very natural other example you could try here for a sextet, right? Which is to take the same sort of thing. So to take a sort of, I think you can still do this, factored, a sort of, if you like, factored 3x3 PSD octonionic matrix and look at its determinant. But certainly you can do this over the quaternions. You could do this in any degree. You could take the quaternionic sort of Gram matrix, look at its determinant. You would get polynomial degree 2D. And okay, at least in the 2x2 case, at least this gap quantity does grow with the number of variables. It just doesn't grow quite enough. But in higher degree, it might. I'm not sure. So I think there's potential for interesting examples kind of coming from that kind of construction, where you're essentially looking at the, if you like, these, I mean, we're really looking at inequalities in the singular values of these kind of matrices, that kind of the convexity is determined by just the singular value inequality, but somehow the sum of squares needs to look at the actual matrices that we're plugging in.